we reached the sub goal, and then I usually make I promise a lecture on something like that. And this time I thought Northern Lights was an interesting topic because obviously I live really far up north in Tromsø. So most of the time you see Northern Lights, unless yesterday you could have had really beautiful Northern Lights. I'll get to that later, but of course it's always snowing here, so you don't really see anything. But yeah. I thought it was an interesting topic to talk about. I thought Northern Lights are kind of cool. I kind of worked with it a little bit before, but yeah. Um, let's get to it. Northern Lights, where they come from, like what are they actually? And in the end, I'll talk a little bit about like if you think they're cool, if you want to see them, what can you do to actually go and observe some? So yeah, I'll go get started. Let me just check the magnets and how do they work. Kind of, a little bit. Anyway, so let's get started. So Northern Lights, also known as Aurora Borealis, that that name comes from the Roman goddess of the dawn. So when the original nomenclature was made, which is Aurora, and from the Greek word for northern wind, which is Borealis. And that kind of begs the question if there's a northern lights, if there's also southern lights. And there also are indeed southern lights. And I think at the end of the presentation, if you don't know already, you will see why there kind of have to be southern lights as well. But yeah, the ones in the north are more prominent because people live further up north than people live in general towards the south. They live closer to the poles in the north than they do in the south. And yeah, in the south it's called the Aurora Australis. Australis, I'm sorry. But from now on, I will probably just refer to northern lights in general as Aurora, because what I'm going to be saying is true for the southern as well as the northern lights, or just Aurora in general. And the earliest recordings of them have been in a cave in France where they've seen caveman drawings, which they think is records of northern lights appearing as far down as in France. And of course, there are a lot of myths and beliefs around them, especially in the medieval times where people didn't know as much as we do now. They thought they were like signs of candles in the sky or heavenly battles or other amazing things. Often they were seen as bad omens, but we of course know that it's just a spectacle of nature that's beautiful to watch. So yeah, where does the aurora come from? And in order to understand where the aurora comes from, we first must understand a few things about physics and about the solar system. So we're gonna go ahead and start talking a little bit about these things first, and we'll get to all the pretty pictures and the interesting stuff will come now and the pretty pictures will come later. So let's get right to it. And first, one of the first things we have to understand is to understand northern lights and where they come from is the solar wind. And if you look at this graphic, you can have a basic principle of the aurora and how it is created by the sun together with the earth and the earth's magnetic field. So in principle, the sun is one very, very large nuclear reactor that in its process constantly radiates charged particles, which is positively charged ions and some negatively charged electrons. This plasma, it hurls outward from the sun in every direction. So it just omnidirectionally radiates these particles, and some of them, of course, radiate towards Earth. And as soon as there's a storm of particles, these charged particles, which we just call the solar wind, as soon as they are hurled towards Earth and they reach the magnetic shield or the magnetic area of the Earth, they interact with it, and they interact with Earth's magnetic field, which then essentially causes the northern lights. But I would like to get a little bit more into the details of the physics on how you get the northern lights, rather than just saying, yeah, charged particles from the sun together with magnetic field of the Earth equal to northern lights. Thank you. I feel like that's cutting it a little bit short. So we'll get a little bit more into physics of what is actually happening here, and how this spectacle of sun and earth works together. And firstly, for this, we can have a little look at the Earth magnetic field. So in principle, the Earth magnetic field would kind of just look like a magnet that you probably know. And yeah, we have, of course, a magnetic North Pole and a magnetic South Pole. But you'll see that the magnetic field is generated by, you don't have to understand exactly where it's coming from, but it's basically created by electric currents due to the motion on convection of molten mixture of iron and nickel in the Earth outer core. And as you can see, this magnetic field that I'm showing here is a little bit different to the one that you saw on the previous slide. And that's, of course, because what we get in practice isn't a perfect magnetic field. It's a product of what happens when the solar wind interacts with the magnetic field of the Earth. So if you take both of these things together, you have these charged particles from the sun together with the Earth having a magnetic field by itself, you get the following. You get what's called Earth magnetosphere, where you have, of course, like again on the left, you would have this cut off from the image. You would have the wind coming in from the sun that I haven't included in here, and then you have the Earth, and you have the magnetic field. And you can see here indicated by some yellow arrows, this is usually where some of these particles can penetrate into the outer atmosphere of the Earth. And so the magnetosphere is kind of like this region around the Earth that is dominated by the Earth's magnetic field, and it's kind of like a comet-shaped bubble, and it's really, really important for keeping us alive on this planet. And so I'm just trying to read chat here. Okay, so far everything seems to be going all right. I'm just trying to copy with chat. Anyway, because if we wouldn't have this shield, we would be getting hit directly by these charged particles from the sun, and that would be, to say the least, quite uncomfortable. And of course, there is a few other planets like the Venus that don't have a magnetic field like this. So solar storms hit the planet's atmosphere immediately, and that, of course, for like an organism like humans, this would be extremely problematic and would not make this planet habitable. So yeah, this magnetosphere kind of just shields us from this cosmic radiation and the erosion of our atmosphere. And the way that this in principle works is that charged particles, they flow along magnetic lines. You can see the charged particles, they flow along the magnetic lines. They don't go perpendicular to it, right? So if you have charged particles coming in here and you have a magnetic field there, they won't cross it in a perpendicular motion, but they will go along the magnetic lines and either get bent around the magnetotail, which is like this tail expanding outwards, or they get directed towards the pole. So under normal circumstances, you don't actually see any northern lights, especially since you will see the sun is here. So this is always the day side. This is always day on this side. And you have some particles that come in here. They often don't penetrate very deeply into this magnetosphere. So you'd have like very faint northern lights. You wouldn't be able to observe them most of the time in most places anyway, unless you live in a place like Svalbard, which is in the very north of Norway, or if you're like a polar bear and you live on the actual North Pole. Because there, of course, you have days where it's dark 24 hours in the day, and then you don't really actually have a daylight side. So, yeah. Here in Tromsø, where I live, you also have some days where it's dark all around, but you rarely ever see daylight northern lights, and I'll explain a little bit why that is later. Or actually, it's better described in a video from my previous employer. So the University of Oslo that I used to work with at before, they made a really interesting like summary video on how all of this works. And just to understand this, much like normal weather, the sun and the solar wind also undergo some increasing and decreasing cycles of activity. We call that space weather. It's an amazing name. And yeah, so a solar storm or solar flare is like when a higher density of particles is ejected from the sun than during average solar wind. So we'll go ahead and watch this like short 5-minute video because they have some really nice way of presenting this. And yeah, it was from my previous employer, so I thought this is a nice way to illustrate on the Northern Lights. Yeah, okay, I will definitely disable that. Okay, I will have to disable all the clowns in the chat. Zap, zap, zap. No channel point rewards for you today. At least not during the lecture. Clowns. Alright, anyway, let's go ahead and watch this video. Hello. Alright, so this is I'll pause this shortly because this is what's called like a solar flare. This is like more than a normal solar wind, where you have like these additional charged particles coming outwards from the sun. And these eddies, these black spots on the sun, you can actually observe. You shouldn't, of course, look directly in the sun, but astronomers can observe these, and they can actually predict events like this. Yeah, and you saw these pictures right there. If you think about how large the sun is, you can kind of like estimate how large these solar storms are. Yeah, you see Mercury and Venus, they don't have like sizable magnetic fields, so it just kind of blows past them. Exactly, and you see some part of the charged particles, they get hurled inwards towards the Earth when this first coupling appears. All right, now some pretty pictures for all you to enjoy. This is totally what it looks like here in terms of all the time. Totally never cloudy, and you never see anything. I'll let this play to the end because credit where credit is due. I'll link all the videos and the sources below the slides as well, and I'll put it up later so you guys can check it out yourself. They actually have a pretty cool project there where they launched a rocket into the Northern Lights at the Department of Physics, yeah, which is of course Physik in Norwegian, where this video was taken from. So yeah, you have the daylight Northern Lights, which are like usually a little bit weaker, and then from the rubber banding of the magnetic lines coming back together, you have the nighttime Northern Lights. And the nighttime Northern Lights are usually a lot stronger than the daytime Northern Lights. And for a while, they didn't really exactly know how Northern Lights work or how this intensity difference comes along, but there's been some new findings regarding auroras in like recent scientific research, and so when I showed you part of the video where you have this reconnection phase where you can, and I'll highlight this, where you saw here these magnetic lines come together, and they showed how the particles, like as soon as the magnetic field lines were connected in the end, the charged particles are always flowing along them. And as soon as they are reconnected, the magnetic field lines kind of snap back, and the particles are dragged alongside magnetic field lines. Like, again, I'm kind of repeating myself, but this is basically one of the most important principles around this. Charged particles flow along magnetic field lines, not perpendicular to them. So they flow alongside them, and then they get hurled back towards Earth, and then they make these are the northern lights you see on the night side, right? That's always away from the sun. That's where you have the tail of the magnetic field. There's always night. I mean, that's how day and night works. But that's the reason why the daylight northern lights aren't as strong as the nighttime northern lights. In addition to, of course, if you have the sun in the background, they are a lot harder to spot. Yeah, I know the camera's in front of the image a little bit, but you see the important part in the left part of the image. And what I found recently is that during this reconnection phase, right, where you where the magnetic field lines snap together, charged particles are accelerated along the magnetic field line. So this was like kind of already known, but these studies suggested that the magnetic field snap back creates some ripples known as alpha waves. And basically what they're suggesting in their research is that these alpha waves have speeds as high as 72 million kilometers an hour. And the electrons kind of surf these alpha waves. And I'll link the paper. They have like some nice graphics on where they explain and show how the electrons actually kind of surf these waves, but that the end effect is, and that's kind of the important thing to take away here, is that they hurl the electrons towards Earth with even higher speed, meaning also higher energy and the ability to drop down further into the atmosphere, because the higher the energy of these particles is, the further they can penetrate into the atmosphere. All right, so yeah, during the video we showed a little bit, or I showed a little bit on what happens during solar storms, and now I wanted to give a little bit of an excursion into what happens during what we would call heavy solar storms. And you get northern lights down to latitudes such as Cuba, but on the other hand, the strongest solar storm that's ever been recorded was the 1859 Carrington event, where a bunch of telegraphing systems were set on fires, and auroras could be seen down as far as Texas in the United States. So when the solar storm is so strong that if you take the magnetic field and it indents it so far, like if it's if you kind of just have like the magnetic field and the solar storm is pressing it forward so far that the protection from the magnetic field becomes less and less. Of course, it won't be gone completely, but when it becomes less and less, you can actually have effects on the Earth. And super strong like solar storms can definitely have effects on it, satellites and electronic infrastructure. And people have speculated if such an event would happen again, like the Carrington event, that there would be a lot of damages caused to electronic infrastructure, because, like, you know, in 1859, sure, there were telegraphing systems, but everything wasn't as interconnected as it is now, and everything isn't completely filled with electronic infrastructure. And of course, we have satellites, and they're much higher than Earth, so they're a lot more exposed. So that could, of course, have just impact, which kind of just brings us to the next topic, which is what I call space news, right? Where I took two articles from the last week, because it just so happened that there was one of these storms, which are called coronal mass ejections, because it's a large mass of charged particles ejected outward from the sun. And SpaceX launched like 49 satellites into low Earth orbit. I don't really know what project they were using them for, but yeah, as many as 40 of those satellites can currently be seen or were seen 2 days ago falling out of the skies. There's some links that I'll show you at the end of this presentation where some people actually recorded satellites falling out of the sky because they got caught by this minor solar storm, you know. So it's this stuff is not only pretty, but it's also important, and can have influence on projects like this. And I'm sure this wasn't cheap for SpaceX. And this solar storm that came up, or there was an ejection of a lot of charged particles from the sun, and that one, of course, hit first Venus and then Earth, and you could actually see northern lights if you live in Scotland or north of Scotland, somewhere like in Sweden or northern Norway. You could have seen really nice northern lights yesterday. In the north of Scotland, there were some really pretty pictures of northern lights yesterday where you usually don't see any. Here, of course, perfect condition to see northern lights in Tromsø, but it was snowing all evening, so no northern lights for me. But yeah, in principle, yesterday was a really, really nice day to catch some. All right, let's get a little bit more into where do the auroras actually come from. So the basic principle is the charged particles per se don't have colors, right? So what do we see? So the atoms in the atmosphere, they're like, oh, we got the incoming, we're getting so excited, and then they glow. All right, so that's a basic principle, and we'll skip the rest from here because it's too sciencey, and I mean, who really cares? No, just kidding. So the glow in the sky kind of basically works as in a neon tube, right? You have electrons of the atoms in the outer atmosphere. This being like a generic atom where like all the non-relevant electrons aren't shown. So you have this energetic particle, which is this charged sun particle, which hits an electron in the atmosphere, in an atom in the atmosphere, and it gets excited to a higher energy state. But in principle, all of these electrons always want to be relaxed. They always want to be in the lower energy state. They don't want to be in a high energy state. They want to be in their ground state. They want to relax. The reason for that is essentially statistical mechanics. So we're not going to get into that. But the important thing to understand here is that when this energy is absorbed, it is then later given back. When the energy is absorbed to excite an electron, it's then later given back. And the way that it's given back is by the emission of a photon. And that is basically light. So you see something. This is where the northern lights come from. So, this is kind of where the colors come from. And now we're going to talk a little bit on what the different colors are, because now we kind of established this. It's established by charged particles that are hurled from the sun towards the Earth, entering the magnetosphere. And we've also established how things glow in general. But what causes the different colors? Because some people might have always only seen a green aurora because that's the most prominent one. If you live really far south and you had the pleasure to see one, you probably only seen a red one, which is due to the curvature of the Earth. Or if you live super far up north and you've seen a super intense one, you might have seen some like violet, pinkish, white glow even, and it just kind of depends on the disturbance in the Earth's magnetosphere. So the aurora can be like super faint or very bright. It just depends on how large the solar storm is, and you kind of just have it ranging from completely invisible to the human eye to even illuminating the ground below in green, as you probably might have seen on one of the like super pretty pictures that then gets later published online, but obviously happens very, very rarely. So, but most often they're seen as green bands, and I'm gonna just show a little bit where the different colors come from, because I personally think it's quite interesting. This is not necessary to understand where for understanding the aurora, but I personally think it's interesting. And you can also be that kind of guy who's like, the sky isn't actually blue; it's just a refraction of the light. You can do the same now with the colors of the aurora if you really want to. Make sure to do it in a nice way. Anyway, yeah. So, in order to understand the different colors of the aurora, we have to understand that the different heights of the atmosphere, if you go from up above to further below in the Earth, going, I'd say going from the upper atmosphere towards the lower atmosphere, you have the atmosphere doesn't quite look the same. It's different. So in the top you have predominantly like monoatomic oxygen. You actually don't have oxygen molecules like you have here what you breathe, but you have like monoatomic oxygen, because the oxygen that's in the outer layer of the atmosphere is split by the UV light of the sun, which splits O2 into oxygen during the daylight time. And there's like not a lot of particles up here. And then in the second layer below, it gets a little bit more dense. You have some nitrogen gases together with the monoatomic oxygen. And the further down you go, the further condensed your atmosphere is, and the prevalent species become heavier gases like nitrogen N2 or oxygen, as you know it, O2, that are in the lower parts of the atmosphere, and they all give different colors. And the way that they work is that we have the spectrum. If you have all the different colors from these molecules, different atoms have different electron levels and can therefore absorb different amounts of energy, and the difference in energy levels then also determines how much energy can be given back, and energy is in general directly linked to the color that you see. I think that's just kind of the basic that's the basic principle. If you want to remember it as different species or different atoms and different molecules make different colors, that's totally fine with me. If you just keep in mind, different atoms when excited with electrons or energy make different colors. That's kind of like all you need to understand or remember here. So if you're in the outermost atmosphere, you have this monatomic oxygen, and it gives this red band, which comes from this part of the spectrum. If we go a little bit further down, we have particles at the top. You only have particles with like not that great a speed and not that much energy, but you need a little bit more energy to get further down in the atmosphere. So the further down you go, the higher energy your particles need to have. So particles with moderate speed and energy reach further down, where there's like more particles, and the green color comes from actually a cascade of events. So what happens is the charged particles hit a nitrogen to ionize the nitrogen, kick out an electron, and that gives you a faint blue photon. But the electron that is then kicked out from the nitrogen hits another oxygen atom and then excites that one as well when energy is absorbed. And when that emission happens, so later the energy is released again, you get a lime green photon. And because our eye doesn't really, it sees two colors and then mixes them together, and it can't really tell them apart. It can't be like, this light is coming from this atom, this is coming from that atom. It can't do that. So you get this like mix of the typical green color that you get from that you see most prominent in most of the Northern Light pictures. You'll have this green color all over, and I'll show you a little bit later as well. It's everywhere. The green color is the most common, and that's why sometimes people think Northern Lights are green, but they're a bunch of different colors. So, you don't need to understand this. This is kind of like an excursion towards the end. I'm sure pretty pictures are coming soon. This is just something that is a little bit more for, because the audience is very mixed between like people that have a lot of background knowledge already and people that know absolutely nothing on the topic. So I'm trying to cater a little bit to everyone. So not every part of this presentation is going to be completely for everyone, and that's totally okay. Like you don't need to understand everything. But I want to explain a few things that I personally think are really cool to the people who are a little bit more advanced as well. And that brings us to the last color. So last but not least, we have this pink color that seems super intense. Have you ever seen it? Actually, I've seen it the first time I came to Tromsø. I went out with my wife and we just were like walking around, and I was just like, oh, this is kind of nice. And we chilled on a bench, and there's like, just, yeah, most intense Northern Lights I've ever seen in my entire life. This seems like a humble brag, but I'm trying to say, I thought this is how Northern Lights always look, and I've never seen them again like that. And then I lived here for 2 years now, and I've not seen lights like this again. So I'm just saying it's a game of chance. Sometimes you get lucky, sometimes you don't. Right, seen them the first time, never seen them again. Does that make me lucky or unlucky? I don't know. Anyway, so this pink light comes from another cascade where you have, instead of this like nitrogen and oxygen atom, because the atmosphere is a lot more dense, you have a lot more, of these diatomic molecules around, and the energy of the solar wind has to be a lot higher to even reach down there. What happens is you have only N2 and N2 plus, so that's a positively ionized nitrogen atom. One electron hits the N2 plus molecule and emits another high energy deep blue photon. So this comes from here. And then the electron hits an N2 molecule where it excites some other electron, and your brain mixes these two, and your brain's like, hello? Your brain's like, yep, blue, red, looks like purple or pink. Your brain's like, yep, pink, but it's lying. It's actually blue and red. So yeah, this is where the different colors come from. If you ever see, see them. So now I hopefully have kind of like interested you in. I've hopefully interested you in Northern Lights, and at least maybe even haven't interested you in them scientifically. You're like, oh, these are cool, I want to see them. So how do we actually predict the aurora? It's the next part, and a little bit of like what I can say about how to maximize your chances of actually seeing something is the last part. So basically every 11 years the magnetic field of the sun flips. So the south pole becomes the north and the north pole becomes the south. Not strictly speaking, but they flip on the orientation. This is of course mixing the words magnetic and geographical North Pole. Fun fact: this also happens to the Earth. It just doesn't happen that often. So the South and the North Pole, they can of the magnetic field of the Earth, they can flip, and that takes around 450,000 years. So and the whole flipping procedure takes between 2 and 12,000 years. So it's like kind of fun fact on the side. So no need to check your compass. It's not going to happen like quickly. And as long as you have a compass, it's always pointing north unless you're like a polar bear again. This lecture is very relevant for polar bears. If you live close to the geographical North Pole, your compass might not be pointing where it's supposed to be, because Yeah, the North Poles aren't the same. The geographical and the magnetical one. They don't. The axis of the Earth and the magnetic field that are completely aligned. They're a little bit off. It's like 15 degrees, but whatever. This kind of switching in the sun, which is the actual point, this switching goes in cycle, and this cycle also incorporates a cycle of completely different intensity of the solar wind. So you have this 11-year cycle in the sun, and you usually have a peak in Aurora 3 years after the sunspot cycle maximum. And so it clears around, and you get more sunspot, you get more solar storms, you get more solar flares, you get higher storms, and the next maximum is projected for 2024. So 2024 should be a great way to observe northern lights. And then they use some real-time data from astronomical observations. The black spots on the sun you can actually see. Of course, not with your real eyes. That's a dumb idea. Don't look into the sun, chat. Please don't do it. I'm just repeating myself, but please don't. And using a spacecraft. And that's called the ACE Spacecraft, known as the Advanced Composition Explorer, which is this. I kind of previously mentioned it. That's where the space news partially comes from. It has like real-time solar wind measurements, electron, proton, alpha particle monitor that gets you all the charged particles. I actually worked on it when I did a internship with NASA like forever ago. I was working with the SWEPAM, which is a solar wind, electron, proton, and alpha particle monitor, short SWEPAM. So these kind of observations, and it sits at this L1 point, is between the sun and the Earth. So it always just monitors the solar wind that is, of course, coming towards the Earth. Because I mean, you don't quite care as much about the solar wind that goes, I don't know, like, let me point outwards this way. You don't care as much about it. That's why we have it here. It always measures the solar wind that is coming towards Earth. But it also records other things, interplanetary shocks and data like that. So yeah, so the observations kind of provide some context for like solar wind phenomena, define structure, and then it makes some prediction. You can make some predictions. All right. So now to the interesting parts, where do we actually see northern lights? And the northern lights you can see in this green zone. If you live in the green zone, you're super prone to see northern lights. And this is again, this is why we often say northern lights, because like, except for penguins, literally nobody lives in this green zone on the South Pole. Like literally nobody lives here, except for like penguins and like some scientists. That's why this is why we usually talk about northern lights and not about southern lights, because there's just not that many people to observe them. And then this like yellow zone, you're a little bit more likely, and in the orange zone, which is like a really large area of Europe, like England, Germany, even and some good parts of the United States, you can see northern lights during solar storms, but you won't see them otherwise. If you live in the like green area, you see them all the time. If there's no clouds. If you live in the yellow area, you'll see them reasonably often, like anytime there's like a solar flare or a bit higher activity. But yeah, what to do if you don't live in? Yeah, what do you do if you're like not a penguin or a polar bear? So there's a few ways that you can kind of stay informed about if you will be able to see it. Probably if you live super far south, and it will happen. A newspaper will alert you about it as well. You can find on this website. This is the space weather website from NASA. or Space Weather website from the University of Tromsø here. They all have northern light predictions that they do every day. Every 30 minutes they have a prediction, and the green zone will tell you where you see northern lights, and I will show you here. This is the important part, the KP index. This is how strong the lights are. If the KP index is like 4 or higher, you're very likely to see something. And the further south you live, the higher the index kind of is. Like if you get up to, so the storm that we had was a KP5, KP6. That was the thing that happened yesterday in the space news segment. That's why you could see northern lights all the way up in Scotland. So if you see this number and you kind of know where you live, you'll be able to figure out when you can see northern lights. If you're lucky enough to live in like Norway or Sweden or Finland, you'll be able to see them more often because KP numbers such as like 4 and 5 are reached more often. Anyway, so yeah, that is pretty much all I wanted to show you. I hope you have a little bit more of understanding where the northern lights come from, why the magnetic field of the Earth is super important, so we don't get bombarded by like solar wind every day, and maybe you even see as to where you have a chance to actually see some northern lights. So let's go to the much wow part. Some pretty pictures. That, of course, I've taken nearly none of them. I've actually taken none of them, but those are northern lights you could theoretically see. I have to make a short disclaimer. They always look much better on the pictures than they look in real life. And those are a few pictures that I've taken from other websites. This is from Senja. Well, this is right around the corner. Senja is like few islands down that way. Senja is actually really close, huh? This is from Iceland, but that is of course cheating. So they of course work here with like longer exposure and stuff like that. I could not imagine northern lights actually looking like this. I mean, maybe they do, but this is amazing. Do we get some slow jazz? Slow jazz with the pretty pictures. I need to find slow jazz first then. Wait, that's my Spotify. Here's some slow jazz with the pretty pictures. I have one more from Alaska, but this is also, I would probably guess that this is a long light exposure where they just collected lights over like a whole evening, or several hours at least. And just to make you a little bit less sad, when my sister and her husband came over, this is kind of what we saw in the middle of winter. So I hope now you're a little bit less jelly. So this is a little bit more realistically what it looks like. This is of course a lot of like light pollution coming. Even though Tromsø is not a big city, you always have a lot of light pollution, even though we drove like 30 minutes outside of the city. This is a little bit if you look away. If you look away from the city, if you look in the other direction, you see things a little bit more nicely. In reality, these pictures are even a lot more intense than what you could see with your eyes, because you have cameras always take much better pictures of northern lights than we do perceive with our eyes. It's a little bit less intense, but this is kind of what it looks like most of the time. It oftentimes doesn't look as on the pictures that I was showing. Tinder pic versus a first date. Yeah, and those are some of the sources and reading material. Of course, space weather, where you can find all the news, space weather news, from New Norge, from the NASA. Spaceweather.com is also NASA. University of Tromsø. That's the newspapers on the Alphen waves. That's the paper that I was part in for the Huntsville thing. Just a shameless plug, if I'm completely honest. But yeah, thank you guys for watching. Thank you very much. I hope you guys enjoyed it.